Hey. Thanks, guys. How are your dreams? Did anyone have any quantum dreams? Entangling dreams? Did anyone imagine that they were entangled with a chair in New Zealand?
Yeah, I did actually.
Yeah. That's good. I'm going to continue on a little bit from some of the things we talked about yesterday. That was more of a deep dive into the physics. Let me tell you a little bit more about the kind of context, almost historic context, that is looking to the past as a means of understanding perhaps where we are in quantum computing. And then we're going to have a discussion with some fantastic people that work right here in the building for Microsoft on quantum computing. And you get to ask them anything you like. I'm going to ask them some questions as well. And we can have a broad discussion, not just about the science itself, but what does it look like to work in this field? What does it look like to be a scientist? What does it look like to make things happen on a grand scale that's going to change the world? Before we get started, any burning question that you must have raised right now in relation to the things we talked about yesterday? Oh. Go for it. And I may not answer it now. But bring it. Okay, great question. Good, yep, let me file that one. We'll come to it. Yep, what was the other one? Yep.
So how does the particles become entangled, and can they be forced into entanglement?
Okay. So let me answer that one now, because it's, I think, directly related to what we covered. The question was, how do particles become entangled? And can they be forced into entanglement? Yeah, so underlying entanglement is really just interaction between quantum, that is, I'm going to say objects again. I mean quantum particles like electrons or atoms, neutrons, in which their wave-like character, their wave function, is coupled, connected, interacting with another wave function. And then, depending on the configuration of those wave functions, you can describe certain states that can't be described as these two entities separate in isolation. That is, that you have to look at the correlations between them. So how do you entangle particles? Well, you have to have interactions between them. And it turns out that in a quantum computer, there is what we call a logic gate, very similar to the kind of Boolean logic that you see in classical computing, like an AND gate or NOT gate, if you've heard of that. Bits flow in, bits flow out. In quantum computers, there is something called a 2-qubit gate, which is a gate that interacts qubits, and it's an entangling gate, a gate that produces entanglement between quantum objects, or in this case, qubits. So part of the way in which quantum computation proceeds is by turning on and turning off entangling gates, choosing which qubits or which particles get coupled to one another and entangled with one another at which sequence in time. That is the whole game in some ways in terms of how you would run a quantum algorithm. You would choose which qubits get entangled with other qubits at which time.
Right.
Yeah. Okay. Yes? No, you.
I'm not super informed on quantum physics or computing, so could you explain what exactly a bit and a qubit are?
Okay. So yesterday what we were saying is that bits, the fundamental unit of information, in binary you can think of as a 1 or a 0. That is the absence or the presence of a single bit of information. We're representing and processing classical information, that is bits, in the configuration of a switch. It doesn't have to be an electrical switch. It could literally be a big mechanical switch. And if you wire up circuits so that switches, depending on whether they're in one state or the other, on or off, can drive other switches. An example would be, imagine I have two switches, and if they're both in the forward state, then they can switch a third switch, but if either one of them is in the reverse state, they cannot. So creating those kind of logic constructs based on the configuration of switches, that is the representation of bits, ones and zeros, we can process information and compute, calculate, and then it's really over to that whole stack of software we talked about yesterday to go from the basic instructions at that fundamental logical level, manipulating binary numbers, up through operating systems and applications and controllers, and like there's a whole stack of software layers that have to then ultimately present you with, that image that you saw on Instagram this morning. But breaking down what it took to get that image, you can bring that back to these fundamental logic operations of bits. Qubits are similar, but they're actually also fundamentally different to transistors that are representing bits. So qubits are also physical in the same way that information is physical. Transistors are in a state, or a switch is in one state or the other. A qubit is a physical object. It could be an electron. It could be some other quantum object in which the state of that object now represents some quantum information. That is to say, it captures both the amplitude and the phase, not just the amplitude. Once you start to work in that complex, that is accounting for amplitude and phase, then that wave-like nature allows for interference, as we saw yesterday, and the ability to process information according to wave mechanics. In a lot of ways, quantum computing is wave computing. Another word for wave computing is analog computing. We're processing information based on analog signals, represented in terms of their amplitude and their phase. Okay, how about we hold those questions for a second? I'm glad you guys are hungry for more questions. That means we're going to have a good discussion, but I'm keen to have my friends also engage in the discussion. I think they'll have some interesting answers for you. This is where we left off yesterday. Let me give you some mood lighting to help you wake up. Feeling awake? How about that? Is that good? We were talking about the different physical implementations that are currently being pursued, explored around the world as platforms for building quantum computers. So that's an unusual thing. For those of you, that have been born in the last 20, 30 years, the idea that information can be processed in any other way apart from the digital electronic computer that you have in your pocket or on your desktop or in your handbag, that feels very strange. But if you go back in history, of course, well, computers were built from transistors, from vacuum tubes. Go a bit further back, they were built from mechanical systems. In fact, I should have shown you an image, see if I can dig it up. A famous computer in the 1960s was built using fluid dynamics. It was a fantastic system for emulating and capturing turbulence in financial markets. I'll show you a picture, I'll dig it up, but it has a big tank of water, and it has that's the Federal Reserve, and it has a pump that takes drip-fed supply from various other tanks and then feeds it right back up to the Federal Reserve again. So that was the taxation system. And it's possible to build a machine that actually processes information, does calculations, by the manipulation, in this case, of the flow of a fluid like water. So that may be really unusual because you think of a computer as something that's processing electronic information, switches, transistors, and pulses of electrical current. But it's important to realize that, well, that's just one particular representation of information. In the quantum domain, we're still exploring many different approaches. We haven't yet arrived at the equivalent of the transistor. Should qubits be represented as the polarization of light, of photons, Or should it be the state of an atom or an ion in an atomic trap? Should it be the spin of the electron? Or should it be, this one's a very unusual one, something that perhaps is storing and manipulating quantum information not as a particle that's localized physically in space, like an electron or a proton or something, but perhaps in a form that distributes that information, what we call non-locally, in a way that makes it much harder for the environment to make a measurement or the environment to observe that particle. We said yesterday that there's this phenomenon of quantum measurement in which the act of making a measurement actually influences a quantum system. And it turns out that what it does when it influences a quantum system is it makes it classical. It makes it a regular old bit. You lose that phase-like property, that wave-like property associated with the qubits, and they turn effectively into classical bits when you observe them. So you want to be able to make a measurement when you want to make a measurement, and you don't want everything else, that is the environment and the noise sources and all the uncontrolled aspects, interactions, to be measuring and observing your quantum system. Because if that's happening, your quantum system's not very quantum anymore. It loses its wave-like character and turns into classical bits. So that topological qubit that you can see there is a very early prototype attempt at trying to see whether there is, in fact, a way of representing quantum information such that it is not locally concentrated in one region of space, but rather separate or non-local, and manipulated in a way that makes it a little bit more immune to that observation effect that leads to qubits becoming regular classical bits. The reason to go into that detail as I did was because that particular qubit is the type that Microsoft is very interested in and has been working on for a number of years. It's an extremely hard problem, and if you want to know just how hard, then you can talk to our panel guests in detail. They'll tell you about their experiences trying to make that thing work. So I've said already a little bit about measurement, that is, readout, how you map the state of a quantum system like an atom into the actual movement of a needle, or, of course, the way it's really done, the result that ends up in your computer and written to a file. But nevertheless, there's a mapping from quantum system, nanoscale object, usually at extremely low temperatures, very close to absolute zero, isolated from the environment, living in high vacuum, in the dark. Somehow we have to detect that and eventually turn that signal as to the state of the qubit into a classical piece of information that you can write down with a pen. That's what readout is. Control, that's kind of in the other direction. Rather than extracting information from qubits, we have to be able to manipulate them, usually with electrical signals, microwave and radio frequency signals. I wanted to give you some context. Often we get asked the question, where's my quantum computer? When do I get my hands on this thing? I want to buy one. How much will they be? Can I get them from Harvey Norman? Are they currently discounted? No, not for a while. If you type quantum computer into your favorite search engine and click search images, this is what you get. That's where I got these images from. I did Google image search. Apparently, this is what quantum computers look like. Just squint a little bit, tune out for a second, you could be forgiven for thinking that you're looking at the machines of the 1940s. And indeed, many of the problems, many of the challenges that the pioneers of classical computing faced in the 1930s and 1940s, those are the challenges that we're facing now, some of them. We face even greater challenges in some ways, but we're back there. It's 1941 in the equivalent kind of technology space. It's very interesting if you want to dive into this sort of historic perspective, you can go and read what people thought about classical computers, what they worried about, what kind of problems they saw. This is the vice president of Bell Labs, which was a powerhouse of innovation over the last 100 years. And Bell Labs was responsible for actually bringing about the transistor. The VP of Bell Labs looked at this issue of classical computing and was freaked out by what he called the tyranny of numbers. There are too many wires, there are too many connections. We start to wire up this machine, connecting one logic gate to another logic gate, and so on. And eventually, when you have enough wires, something breaks. The probability that a cable or a connector is going to fail, well, that probability is finite. It's not zero that it's going to fail. No matter how small it is, once you have enough of something, that becomes a problem. Those issues largely got solved with the invention of the integrated circuit, that is, printing effectively transistors on a chip, connecting them in a way that doesn't require these macroscopic bulk, meter-sized cables and connectors. But quantum computers are still in the regime where we're trying to connect things like those classical machines. We're trying to scale them up. We're trying to go from the basic demonstrations. Imagine something like, I've got a few transistors and I can show that they can take electrical pulses of 1 and turn it into a 0, something like that. We're trying to connect those and wire them up and scale them up into a circuit that's actually useful. And we don't yet know how to do that. We're trying to figure out whether quantum computers are possible. Do they scale the way that classical computers do? Billions of transistors. Can you have billions of qubits? We don't know. Are they like neurons in your brain? Can you connect them like that? We don't know. You have 100 billion neurons in your brain. Does that mean that, well, probably you can have 100 billion qubits? Are brains like qubits? Are they like quantum computers? Probably not. Or are they more like cars, that once you get enough of them, it's a giant headache? It becomes very difficult problem to solve the scaling of traffic. We don't know. We're trying to find out. We're trying to actually look forward to how these types of systems, as the complexity grows, how the new challenges arise. Are there what we would call emergent phenomena that only switch on at a certain level of complexity or scale? Where are my 3 anointed? 1, 2. There you are. Yeah. How are we doing? What is what? Who? Oh, yeah. So don't tell anybody, but I recycled some slides. So, that is a measure of how well a qubit can be controlled or how well it can be measured. So if you're talking about the measurement fidelity of the qubit, that would be a measure of how well you can detect its state. With what precision? Yeah. Okay. That's what quantum computers look like today. That's one of the most scaled up complex quantum computers around. That's Google's machine. They call it bristlecone. It looks pretty messy. It's filled with wires. The thing you're looking at is actually a refrigerator. We have a lot of them in this building. And where that guy's got his hand, once that thing is all buttoned up and the air pumped out of it, once you start the cooling cycle, a couple of days later, where he's sort of touching, that region of the refrigerator gets to a temperature of order 10, 20, 30 millikelvin. Millikelvin, 1/1000th of a degree above absolute zero. That's the temperature you have to work at to be able to do these experiments. Why is that? Yeah, it's related to, first of all, the energy scales. We're trying to manipulate things that have energy scales that are really small relative to the thermal energy. Okay, so many of you guys have doing physics at school know about kinetic energy, half mv squared, or potential energy due to gravity. There are energy scales associated with single quantum objects, and we're going to get swamped by all of the jostling thermal motion unless we cool them down. Yes?
When you cool, say, liquid helium down really, really cold, it becomes a superconductor?
Yeah, basically. It becomes something we call a superfluid, which is basically a superconductor. Yeah, absolutely. True. We use that phenomena actually as the basis in some ways of cooling these devices. That superfluid transition in liquid helium is part of the story of the cooling process. There's more to it than that, but yeah. Yeah, it's not sufficient just to focus on the quantum part and quantum information processing. You also have to know something about superfluid helium and cryogenics and electronics and lithography and nanofabrication and, as I said at the start of the last lecture. Okay, so a few challenges. I just wanted to throw up one slide just to give you a bit of a flavor of the challenge ahead. Here is not quantum computers, but regular classical computers. This is a prediction that came out of Intel in 2004. Have a look at what's plotted. Whenever someone puts a graph on the display, you should take a moment to look at the axes. So what's plotted here is the power density measured in watts per centimeter squared, how much heat you're generating, how much power you're dissipating. And this is years from the 1970s through to 2010. Now, this is from 2004. So 2004 is like here. And then they sort of made some extrapolation as to what the heat density was going to be. These numbers refer to different processes that Intel has manufactured. So already, actually, the heat density of our CPU, even at a level of just above 486, like Pentium, already has a heat density that is comparable to a hot plate. Which makes sense. If you put your finger on it, you'll burn your finger if you don't have a heat sink on there. But look at these insane predictions that the heat density is going to exceed the surface of the sun by 2010. Well, that didn't happen. The years went by and your computer didn't turn into the surface of the sun. Why is that? They just put a speed limiter on your processor. It turns out that the power dissipation, power being energy per time, the power dissipation you can reduce by just dissipating the same amount of energy over a longer time. If you slow down the clock, you would dissipate less power. So you can look here, this is transistors per chip. This is years. This axis is not shown, but the important thing is that if you did see this axis, if you focus on the clock speed in red, this is measured. I can tell you roughly what it is. Let's see. See if I get this right. I'm going to say 1 gigahertz is about here, 2 gigahertz, 3 gigahertz, 4 gigahertz. So around about 2004, they just started limiting the clock speed. They put a brake on it. And that curve has remained flat. This is pretty old, but that curve has remained largely flat to the present day. So you have a heat problem. This is interesting. Microsoft has a heat problem too because it builds data centers. If you're accessing something on the internet, it's usually accessing hard drives that are in a data center somewhere. And those data centers run on computers that are getting hot, and that costs a lot of money because you have to cool them. So one approach is, well, what if I put a data center in a tank and I'll drop it into the deep ocean where there is a cold current, and I'll have a pump that just pulls cold water through the thing and heats up the world's ocean by some small fraction. Well, that's cool. You can also drop them in around cities, because cities are on the coastline. That doesn't overcome this fundamental issue, but it's interesting just to see the extremes that companies like Microsoft are going to in order to be able to address that problem. Quantum computers are no different. I'm not going to go into the detail here. This is what we're looking at the moment. I just want to make the point. There was a good question yesterday about how does a quantum computer really look? There's a quantum part, there's something to do with qubits, but you need a lot of other instrumentation and electronics and subsystems to build out a machine. And that's exactly what we're working on here. So, if you haven't got the point already, we don't yet have a quantum computer, and in fact, we're probably some years away from one. We're still in an era where we're looking at raw data the way that high-energy physicists looked at data in the 1960s. This is a bubble chamber, and the way in which particles like, let's see, like a pion or trying to get the year right. What else? Positrons. Those things were discovered by looking at the trajectory that particles left when they streaked through a chamber where there was basically a layer of fine bubbles, like the kind of condensation you might get on a windscreen. Turns out then when a particle rips through that, it nucleates the bubbles and leaves behind a visual pattern that tells you about the properties of that particle. The trajectories that you see are related to the momentum or the velocity of the particle, and whether they spiral this way or that way in a magnetic field, of course, is determined by whether the charge is positive or negative. It's kind of interesting that you can back out the details of a fundamental particle from looking at its path that it leaves in a bubble chamber. That's a little bit like where we are today with quantum computing. We're trying to build devices that allow us to try and understand what's going on. But I think over the coming decade or so, this whole field is going to make a transition, and you guys are going to be at the center of that. We're going to move to the way in which high-energy physics does business today. No one's looking at bubble chambers. Computers are doing a lot of the analysis, capturing the data, sifting it, and we're going to need classical computing in a way that is really powerful to even be able to start to build our quantum computers. Eventually, we'll have some kind of quantum computer, some kind of quantum machine, and you could ask, well, what are you going to do with it? We talked about all these grand societal problems and challenges. I think those things will actually be the second thing we do. The first thing we'll do with a quantum computer is use it to make a better quantum computer. Okay, so there's going to be a lot of bootstrapping, first of all, between classical computers that ultimately leads to the first quantum machines that are then used to understand how to make better quantum machines. I'm sort of, yeah.
So what I've taken kind of from that is that it's really interesting. And then so the field is currently a bunch of extremely intelligent people with extreme high-tech equipment playing a game of trial and error.
I think that's not a bad summary. Yeah.
Okay. Gotcha.
Is that going to be the right approach for building out a machine?
Yeah, that's what I was wondering.
Good question. Save that question. Okay. That's sort of all over the place in terms of we've touched on, half a dozen different aspects to this, but I'm trying to give you, I suppose, just a bit of a taste of all of the interesting issues. If you're someone that's interested in physics, there's tons of physics here. If you're interested in how technology works, software. We had a question yesterday about AI and approaches to machine intelligence. All of that area of research is going to be important for understanding how to get these machines up and running. Lots of opportunities, many career trajectories. So to tell you a little bit more about the options and the possibilities and what life can look like, I've got two guests here who are going to come up, and we're going to sit here. We'll turn on the lights. Let me introduce them. So I've got Maya Cassidy and Erin Hurbi, who are both from Microsoft. Pretty lucky to have them here. I'm going to put them on the spot and have them introduce themselves in a way. Why don't we get right into it? So, Maya, what do you do here in this building, and how did you end up here? From being somebody more or less sitting on that side of things, sitting in the audience, what did your life look like that took you from sitting in the audience, listening to people talk about research, to actually doing research for a large technology company?
Okay, hi everyone. My name's Maya Cassidy. I'm a principal researcher here at Microsoft Quantum in Sydney. I work on scaling up these topological qubits, so taking one experiment and working out how we can make thousands or millions of qubits all work together. It's a very diverse problem. It involves materials, like a lot of chemistry, nanofabrication technologies, physics measurement, cryogenics in these dilution refrigerators, and then on top of it, software, AI type things to try and then feed back to the materials and work out not how to do just trial and error, but make some intelligent choices about how to progress the technology forward. So as David said, I was probably very similar to you guys about 20 years ago, sitting in the audience of schools like this in high school. I actually went to high school about 3 kilometers from here, just across the bridge in North Sydney. And what took me from there almost all the way around the world to come back here? So I was in high school. I would have to say I really didn't know what I wanted to do. I was really good at, I would say, science, maths, but also actually really good at social science, economics, geography, history, that type of thing as well. I was probably, like on paper, even better at that at school than I was at maths or physics. And you know, you take subjects, you take a wide range of subjects, probably you know, as you're leading up to your HSC or your final exams at the end of year 12. And I just took a broad range. I had absolutely no clue what I wanted to do. I think
What tipped it?
What tipped it? I would actually say that nothing tipped me into science. I actually didn't do science at university. I did electrical engineering. What tipped me into that? Probably the fact that I didn't get into medicine. I think the year that I graduated, the score to get it directly into medicine was 99.7, and I got 99.2. So I was a failure. And so I didn't go and become a doctor. So I applied for a whole bunch of scholarships because I figured the best way to go to university is to go where they pay you. And I was given scholarships both from University of Sydney and UNSW to study engineering. And I chose, I went to UNSW for no good reason, and I enrolled in electrical engineering. I had no clue what it was. I'd never written any code. I didn't even know what a capacitor was, I think, at the time. And I turned up like fresh, first year electrical engineering on a scholarship and was completely overwhelmed by what was there. And I think I continued to be overwhelmed for several years. Part of the scholarship that I did get actually allowed me to go and work every summer at a range of companies around Sydney. So I worked at Cochlear, where they make hearing implants. I worked at Telstra. We worked on actually heat problems in data centers, but in like the telephone boxes that sit out in the middle of the desert in Australia. And I worked in the undersea data communications for Alcatel. So these were sort of summer jobs. And to be honest, I really didn't like any of them. And I thought, I don't really want to be an engineer. You know, I was okay at coding, okay at sort of like circuit design stuff, but it wasn't really what I was interested in. And almost by accident, I enrolled to do my honors degree in a group, well, like to do my honors project in a group that David was actually part of at the time in quantum computing at UNSW. And this was middle of 2000s, 2005, I think. And
I'm not that old.
and they were, they were building some of the very, very first qubits. So here in Sydney, in Australia. And that was something that actually completely changed my outlook on everything to do with science, with physics, and what I wanted to do with my life. And before actually doing that honors year, I had spent a year doing a Masters of Finance. I was working also, I had done some work in finance, but I started my honors, started working hands-on in the lab, and really, became excited about the range of things that were possible. And what I really liked was taking something and building it, actually with your hands, and assembling all the bits, and then understanding every bit of it, and then measuring it, and then making it better. I really loved that process.
How many of you would say that you don't have a precise, clear, exact goal of what you're going to do? Roughly, but it's still a work in progress. Great. How do you feel having heard Maya's story?
So, it gets even better because I still didn't know what I wanted to do at the end of my honours. And I thought, well, living in Sydney, well, you've got to earn some money. So I go in and work for a venture capital fund for 6 months, and I hated it. Talk about hate. And all I wanted to do was be on the other side. Instead of building Excel models, be on the other side of the table inventing things. So I actually went back and started a PhD, and very soon after applied to go to Harvard, and somehow managed to get in. I still don't know how. But I went and did my PhD, my master's and my PhD at Harvard in applied physics, as funded once again, important to get some money along the way from the Menzies Foundation. My PhD also wasn't in qubits. At that point, I was really interested. I was actually, I think, maybe a little bit frustrated by the slow pace of progress in quantum computing at that time. And me being young, naive, probably, thought that things should happen much faster than they did, and I was frustrated, and I thought, I'm not going to work on this anymore. I want to break. I want to work on something new. So I did my PhD actually in medical physics, trying to invent new types of nanoparticles that could attach to, say, cancer cells and be used for medical diagnostics. That was super fun, exciting. Once again, taking things from the materials, building them up, putting them through some process of trying to actually get them to do something, understanding a lot of data, measuring them in an MRI machine, putting them inside a rat, and watching the rat light up. That was all stuff I did in my PhD. And then when I got to the end of that, I thought, well, okay, am I going to take this technology to market? Is this something I should be doing right now? And I have to say that I made the decision that probably I wasn't the right person to be doing that alone at that time. One person is not going to disrupt the entire medical imaging industry. So I actually went back to qubits, and I moved to the Netherlands as a Marie Curie scholar to work for Leo Couwenhoven. And these topological qubits had, the concept of them had really just appeared. There was a theory proposal, I think, in 2010, and an experimental demonstration of how to make them, roughly, to show some signatures of them, 2011, 2012. And so in 2012, I went to Delft, basically excited about quantum computing again, that there was this new type of qubit, a topological qubit, that was maybe not going to have some of the same problems that we'd seen with regular qubits for the preceding decade or 2 decades. So I was there for four years, working a lot on new types of qubits, new materials, also a whole range of other new physics things that I think, so superconducting electronics as well, so how to control or read out these types of qubits. And leading a little team of graduate students and postdocs to do science. Then in 2016, I think, so we had been funded by Microsoft to do this real research since 2012. And in 2016, Microsoft made a decision to try and, I guess, bring a lot of that research in-house. And so they hired people like David, and they also hired me. And so I was lucky enough to be able to get a job back here in Sydney. It was super important for me. I have little kids, and it's something you think about in your life as you're maybe looking forward, forward at your career. Is it's not just about the work; it's also about your life and how to balance, what you want as a person, your family, with your career. So this was a super lucky situation to be in, to be able to do, I think, some of the best research and technology development that's possible in the world, and do it in Sydney, which I think is one of the best cities in the world, and happens to be also where I grew up. So
Fantastic.
Here I am again, around the world, I think. It's been a very diverse experience.
Fantastic. We're going to hear from Erin as well on a similar line, but are there questions from Maya regarding her life story? Yeah.
I feel like it's quite a big and difficult decision to make, starting back from your PhDs and doing medical physics and then going back to qubits. So how do you manage to do that?
Yeah, you're right. It's always, I think every time you switch fields, it's a big challenge. It's something that I think it's the only thing that holds you back or sets you up for this is your attitude. Keeping an open mind, deciding that you want to be someone who learns new things. Every field was new to someone at some point. This concept of being an expert, I think, is you've got to really think about the only way people were experts in anything is they started at the very beginning and they became that. Nothing stops you becoming an expert in something new or different.
And don't forget about de Broglie's matter wave discovery there that we talked about yesterday. There's a role for just blind guessing and serendipity. We need outsiders, not just people that are, long trained and experienced in a particular field, also with the blinkers on. Yep.
Do you feel that the time you spent in health was in a way sort of wasted after you switched degrees to something that was entirely different?
I don't think any of, okay, maybe I want to always look on the bright side. I don't think any of the time I've spent on anything is wasted, really. The really interesting thing to realize is that actually how similar a lot of technologies are. And so things that you learn in one thing are actually pretty applicable to the next thing as well. Like even the physics of what I was doing in this medical physics, it looks a little bit like the physics of a qubit. It's just instead of individual electrons and individual nuclei of atom, it's just a lot of them. But we were doing exactly the same types of control pulsing of electrons and nuclei in medical physics as people do in qubit physics. And so one reason I think that I was able to enter this medical physics research and be successful within a relatively short period of time was my background in qubit physics.
Great. In the front here. Yep.
So when you were doing your engineering and you were finding like the work experience you were doing not like super engaging to you, but obviously it takes people time to find their niche in that area. What kept you from deferring or changing your course that you wanted to do?
Sheer stubbornness. Honestly, I'm quite stubborn. I don't like quitting things. I like completing things and then saying that's done and I'm not going to do that again, but I don't like quitting halfway. I I think also the great threat from my parents that they were, they were going to go basically disown me if I didn't get a degree. They were actually the big reason I never actually did a science degree, because they thought I would never get a job as a physicist. They both are PhD scientists and gave me their expert opinion that it was a complete waste of time. I think I've maybe proved them wrong. I'm still not sure.
Was there a question? Yeah.
In terms of your research, your PhD, would you ever consider commercializing it?
For sure. So we filed a bunch of patents at the time and even licensed them to venture capital funds, to a venture capital fund, and they, together with a group at MD Anderson Cancer Center in Texas, actually started doing more commercial work on it. It's actually, what I realized was my place in that research was kind of gone. My place was the person who took it from a concept, crazy, sketch on a blackboard, to the first working prototype. It wasn't someone who then took it from working prototype through clinical trials to become a product. So I think that was something I guess I realized at the time. It takes a different type of person to do the beginning bit than it does to take the end bit. And I'm much more of the beginning type of person.
So let's hear from Erin, and then we're going to come back, because save your questions. I think it'll be interesting to hear how stories can be different, and the questions that you have may actually kind of be captured by both these guys. So I was thinking of who I could get to talk to you, and I wanted people that came from various different backgrounds and ended up doing different things, or ended up doing the same thing but from a different perspective. So I asked Erin to join us. So over to you. Tell us about what you do here, what your role is here, and how you ended up here, and where you started.
Yeah, absolutely. Hi, guys. My name's Erin Hurbi. I guess that's kind of an interesting segue, because I'm the other kind of person where I think if you just did it once, it might have been a fluke. And so I started also out in engineering. I'm originally from the US, if you can't tell. And so some of this talk about high school and tests very much confuses me. But I went to undergraduate in the US at Carnegie Mellon and studied mechanical engineering. When I was probably y'all's age, I really didn't like the history and the English, and I really liked physics. So I studied engineering because I was like, okay, yeah, I can get a job. And my parents liked it, and I wouldn't have to write papers. That was maybe a little short-sighted. I'm realizing how much fun I actually really like reading and writing papers now. But so yeah, I went and did mechanical engineering. I love physics. I don't know if you guys like figuring things out. I think you're all here because you like science. I really, really loved Newtonian physics, and just couldn't get enough of it. So mechanical engineering is basically a lot of that. And within that, I really sort of gravitated to heat transfer and fluids and the things that, like the fluid computer thing you're talking about, I love that. That's so cool. I love things that you can kind of visualize and you can see how it works, and you have like an intuition for how things move and how things happen. And so that mechanical engineering was kind of like that. And similarly, I had a bunch of really odd jobs. So my first internship, I was working at, I also really love, you guys ever seen How It's Made? Yeah, okay. I was one of those kids who would like sit there and watch that for like 6 hours straight. So a lot of my work has always been in manufacturing, or like trying to get the things that Maya might make and make a lot of them. Make statistically significant quantities of them, like make them over and over and over and over and over again the same way each time. And so I had a lot of jobs in manufacturing. So my first job was actually at a frozen food factory. Turns out they need engineers literally everywhere. And it was so cool watching just equipment do things over and over and over again. And even if it's making something like frozen chicken. And then eventually I got an internship at Microsoft working on reliability engineering, which I don't know if you guys know much about manufacturing. But stuff breaks, and there's a whole field of engineering around breaking stuff for fun, and then taking data on it. Figuring out how people break things. I literally had a job where we would put a phone in a big bucket and roll it around over and over and over and over and over again until it broke, and took data on it to make the designs better. So trying to make them more robust, focusing really on the engineering of that. And then I got kind of bored with that and moved into augmented reality. So I work at Microsoft. I've worked at Microsoft for a long time. Have you guys heard of a product called the Hololens? Anybody? Yeah, okay. So I built those. Slightly different kind of manufacturing, but a really cool kind of computing. And if you haven't heard of it, it's augmented reality. It's like a headset you put on your head, and it like displays real-world locked holograms that you can then interact with and like touch and grab and all sorts of stuff. Really, really cool. Just a fascinating sector of technology to work in, and so I wanted to work on something cool, and that was cool. For that, I did a lot of like heat transfer thermal development, so the stuff David was talking about, where you have a chip that's the same temperature as not the sun, but pretty close. I mean, they're pretty hot. How do you like put that right next to someone's head without burning them and dissipate that heat? So really practical problems like that I worked on. And then I got bored with that again and realized that there was some work to be done in quantum computing within Microsoft. And one of the fun things about having a technical background is you can kind of just jump from technology to technology or sector to sector, because like Maya said, between medical and quantum, a lot of the stuff is the same. The way you do things, the way you solve problems, the way you think is indelible, and it's the same throughout every aspect of sort of science and technology. So then I moved over to that. So currently I'm working with this lovely team of researchers, no longer in the deep technical aspect, but now I'm working as their program manager, trying to make sense of what they're doing and then feed it back to a corporation, and try and understand what the problems are that they're facing and how to help them solve their problems better, how to sort of clear the path, prioritize, understand what the end goal is, and help everyone get to the place that they need to be in. So even if you do have a technical background, that doesn't mean you have to do technical things forever. You can go back and forth and try new things. And I've been doing that a lot. And now I'm here in Australia doing exactly that. Yeah.
Fantastic.
So it kind of seems like a theme for a bit of this school is that you don't have one career for the rest of your life. You have 3 or 5 or 10, and that's cool. And whatever you end up doing straight out of high school doesn't define what you're going to be doing when you're 25, when you're 30, when you're 40, on and on and on, which I think is cool. All right, so we'll take some questions from guys. Maybe any questions specifically for Erin on that? Anyone? Yeah, Alex?
What do you think was the coolest thing you worked on in your time at Microsoft, and why?
I think, well, the quantum computing stuff is pretty cool, but...
Literally.
Cool.
From a technical perspective, working on next generation like thermal technology was really, really cool. It's really fun to work on problems that are really unique. And I think with the HoloLens being, the constraints being both human factors and engineering and all of these like insane boundary conditions, like it has to be a certain weight and it has to be really strong and it has to meet all these criteria that are really, really stringent. Solving those technical problems was probably the most interesting thing, because you wind up, when you're really constrained in an engineering problem, you wind up with really outlandish solutions. And it makes for a more fun experience. Like designing something to a spec that's not interesting is not super fun. So yeah.
Yeah?
Have you done any like further tertiary study after your undergraduate?
Nope.
Anna?
How did you end up in Australia? Because
So I used to work in Silicon Valley. So Microsoft has offices, obviously in Seattle. Redmond is the headquarters. I worked there. I've worked in San Francisco and Silicon Valley area. It was just an opportunity to work on something cool that happened to be halfway around the world. And like Maya going to the US and then to Europe, like I'd pretty much move anywhere for a cool job. So.
Also, if you have any questions that you don't want to stick your hand up and ask, please just send them down to the front and I'll collect them. But yeah.
Which parts of electrical and mechanical engineering did you both like and dislike the most? So going to electrical engineering, and I don't know if it is actually the thing I want to do or not.
Okay, so I think electrical engineering is this like huge, massively diverse field, even within its own subject. You can do things at one end of the spectrum. I would say, like, if I look at what my friends did in electrical engineering, a lot of them became power engineers. They then worked in mining. They worked in high voltage transmission for Energy Australia, making sure that the lights go on, in solar cells. Some people worked in microcontroller design, or studied microcontroller design, digital or sort of computer engineering type stuff. Other people, signal processing, like compressing images, like at UNSW, one of the people that invented JPEG is actually a professor there. Some people on device physics, but in I guess a commercial sense, working on photovoltaic cells, transistor physics.
What did you like?
I liked. What did I like? I liked. I think anything. Yeah, like the boundary between physics and engineering. And the more physics I went, the more I liked it even. But this is just me. So I wouldn't take my experience, my likes as what you would like. I think there's a huge range of opportunities in electrical engineering, and it's all super interesting. And you can take those techniques, like you can take what you would learn in control systems engineering, you can apply that to financial markets. It doesn't have to be to an electrical system. It's a real foundation degree.
Yeah, I think it's important to figure out, like I went into mechanical engineering and I didn't actually get to pick an engineering degree. I got into the engineering school and then I had to pick, but I really had no idea what it was or what people used it for. And maybe y'all are probably a lot more advanced than I was, but there's also massive in scope, and even the stuff Maya's talking about is like a really small percentage of what you can do with that technology and that information. So I would encourage you to go out and see if there's an industry that you're interested in that has that type of skill set in it, because I think it's far more worthwhile to find a meaningful application for your technical knowledge than to just churn through. I know how to code, so I'm making whatever app people want me to make. Figuring out what you want to do with those skills helps kind of guide you. You'll like it if you like what you're doing with it. Yeah.
And all of those kind of engineering schools and skills are fairly transferable, and there's a lot of really universal mathematics and physics that go into different engineering fields. So really it's something where if you find yourself halfway through a degree and change around, it won't be too much of a deal. And as we've shown, you can start doing one thing and then don't even have to really go back to school and end up doing something completely different. Excellent. So maybe some questions for everybody, for the whole group. We'll head up the back. Sienna, I know you were asking one before.
Just a question involving how to work out your career. So I've got a lot of advice that is, work out what you want to do now, and then you'll have a steady way to go. But you guys are more this seems fun, this seems interesting, and then sort of build your career off that. If the old strategy is looking to just a streamlined approach, is that the new strategy? Is just doing what's fun?
I don't know, if I would say I've made the right approach. It's just an example of an approach. And I think, having fun, how do you define fun? For me, fun is creating new things and that success cycle. It almost wouldn't matter what I was doing, and I would still call that fun. But in terms of how I sort of now arrived at different spots, working with different groups of people and different projects, it was actually really about the people and finding a group of people each time that I was excited to be around and wanted to turn up and be part of the experience every day. That was the thing that made me switch and join different groups, move to the other side of the world, move again. It was actually all about the people. At each stage I had many, many opportunities of paths to go, and the path that I chose was the one where I felt the most synergy with the people on that path.
I'll maybe make one comment. I think when you look at fun, and this is true of career choice as well as many other areas of life, one thing that I think I've appreciated as I've gotten older is that you have to average out or integrate out over a larger period of time. So, for instance, what's the funnest thing you can think of? What's something super fun? I don't know, skydiving. That's usually fun. People that do it for other reasons, it's fun, right? Okay, so that was fun. How was the plane trip up? Was that fun? What about packing? Was it fun to get up at 4 in the morning because the plane takes off at 6 to do the skydive? Was that fun? Was it fun going to the bathroom on the way? Was that fun? There's an end goal, and that happens in the future, and to enjoy that experience and to have that fun and that satisfaction, there's also a number of other steps that have to happen. And I think it can be challenging often to see that bigger perspective. If you're studying for an exam, you're thinking, well, this is not fun. But, remind yourself that time moves and you're on a path, you're on a trajectory that is taking you to something that will bring a lot of fun, satisfaction, and other things that you may want to value. Your ability to see the things that you do in that broader context rather than living in that moment, I think, is something that is helpful.
Yeah. So, if your definition of fun is jumping back and forth between careers, then go for it. If your definition of fun is focusing on something and doing that, then that's probably for you.
We've moved into a discussion around careers, which is great. You can keep that coming, but don't be constrained by it as well. These guys are experts in making quantum computing a reality, and I want you to also have the opportunity to ask them those challenging questions. We had one up here that I haven't forgotten, which is, how about the Marvel quantum universe? Do you want to give us some more context?
What did he portray? What you guys think it actually is? Is any of it actually accurate, or is it just comic book
Marvel universe.
Can we become very small and time travel through the quantum realm?
So maybe I'll start, but these guys should chime in. We're going through a hype cycle at the moment in quantum computing, but that's actually part of a larger hype cycle in pseudoscience in general. And the word quantum means anything you want it to mean in that kind of context. And it's amazing you can actually look this stuff up. The number of companies, businesses that have now used the word quantum in some way is skyrocketing, from laundry detergent to
TVs.
Yeah, it's all quantum. And it's a high-tech word that sounds cutting edge. It does have, let's not, I think, ignore that there are deep, interesting philosophical, metaphysical questions that emerge from the interpretation of quantum mechanics. And that's an area that is ongoing research. We don't yet understand the reasoning or the implications associated with the foundations of quantum mechanics. All the bizarre things that we talked about yesterday in terms of quantum entanglement and voodoo and what does that imply about the world, and who am I, if I'm entangled with a chair in New Zealand, am I still who I thought I was? Am I in? It's not like humankind has all the answers to those questions. We're transitioning from, what we would define as science, as physics, insofar as these ideas can be tested in experiments, into things that cannot be tested, and move into a metaphysics realm. But I think it's super important for you guys to realize that that frontier of knowledge, there is still a dense fog ahead of us. We are still trying to understand the implications of the experiments that we're doing. Like, the experiments that are happening in this building throw up really deep philosophical questions. And how to interpret that, it's a job for someone else, but it's a fascinating area, and I think as we start to build out this technology, we're actually going to come really hard up against some of those interesting philosophical questions. How many of you have heard of Schrodinger's cat? Okay, so it's actually one of the most misunderstood phenomena in quantum physics, and I've even seen quantum physics lecturers, misunderstand what its original purpose was. If you read the original papers by Schrodinger, it's not trying to tell you something about superposition. What we said yesterday about peak and trough coming inside, it's not that you can have an object in superposition at two states at the same time, dead or alive. The point of the Schrodinger cat experiment, it's a thought experiment, was to say, okay, we have this description of reality at the level of electrons and nanoscale quantum objects like atoms, but I don't see people or macroscale objects like cats obeying those laws of physics. Is there a transition from the quantum realm to the classical realm? What determines that transition? And would it be possible to even engineer a macroscopic, cat, an object the size of a cat, that still obeyed those fundamental laws of quantum physics? And so, it's a paradox that Schrodinger was using to, I suppose, shed light on the disconnect between classical physics and quantum physics, and that there must be a transition as you make objects larger. We still struggle to really understand that transition from quantum to classical. Building a quantum computer is building a Schrodinger's cat. It's a macro scale, like it will be an object that is so large and complex when you have billions and billions of qubits. People talk about, I'm going to put 1 billion qubits on a 300 millimeter wafer. Well, I can see a 300 millimeter wafer, and if that's got 1 billion qubits that are entangled with one another, I really have a macroscopic object. It's not a quantum thing anymore. It's not measured in nanometers. The thing is huge. The degrees of freedom are enormous. It's super complex, and yet it's going to obey entanglement, superposition, quantum measurement. Such an object has never existed. And it pushes, I think, limits in philosophical understanding, because it takes us exactly to that realm of, like, am I entangled with a chair in New Zealand? Which we've ignored and thought, well, we're talking about electrons. We're not talking about people. Well, a quantum computer is actually a pretty large, complex object that starts to resemble a person. So stay tuned over the coming decades as, I think, not just fundamental physics, but metaphysics and philosophy and religion, and all of these areas of the humanities, I think, are going to come alive as this technology turns into reality. Sorry for the rant.
That's okay. I have a question on paper. What did you do in the labs yesterday? On a day-to-day, like specifically yesterday, can you guys elaborate, the three of you guys, on what happened yesterday in the office?
Erin can show you some objectives and key results and show you the exact status of what was done at what time.
So I was in the lab yesterday. I actually went into the clean room. I don't know if you've been downstairs one level.
Yes.
And
I think we will be, but not
you will?
yet.
Okay, so you'll walk past these big windows and you'll see people in white suits. The suits are not there to protect the people from the thing, it's to protect the devices from the people. Because what we get, people are dirty, our devices, we're talking about nanometers, you can think your hair is on the scale of tens of microns thick, your skin particles, dust, also tens of microns. They're going to come and smash your qubits. And you won't make any, so that's why people are wearing suits. So yesterday I was in there in a suit. I was operating one of the machines to deposit some silicon nitride dielectric, and Then I was also operating another machine called an atomic force microscope that basically takes a little tip that's nanometer scale once again and goes tap, 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 and maps out the nanoscale sort of profile of one of these devices.
So how do you decide to do that yesterday? Like, what's the process to getting behind that machine and operating those buttons to tap, tap, tap?
I was there to help one of the people that I was working with because they are still learning about how to do this, so I went down to help a bit. Why were we doing it in general? It's the next thing on the list to do. So we actually we're trying to make a new type of wafer or a new type of device. And we need to know when we etched our silicon nitride layer, did we actually get to the bottom of it or not? And is there any residue left or not? And so we use this atomic force microscope to try and answer that question.
So is that the thing, Erin, where that's your job then to go through and
To make the list of all the things that need to get done.
make the
Yeah,
list and
pretty
then
much.
they go through it in order? All right.
Yeah.
Okay.
And you don't want to be entangled with dead skin. That's the end goal.
That sounds very sci-fi. All right. Lots of questions. We haven't had one from over here yet.
Just in terms of entanglement, like, what is the limit to entanglement? How many objects can a given object be entangled with at a given time or forever? Let's say.
You want me to take that?
Sure. Well, I would say we don't know yet. Honestly, humans are really just starting at this problem. Maybe one thing to say is there's probably a role for entanglement in biology, and that would involve massive numbers of things. But we don't understand it. It's just a hypothesis.
So I think it's actually, turn that around. I said earlier that entanglement is generated by interaction. Quantum objects interacting with other quantum objects become entangled. And then they become classical. They look like the quantum physics, the wave-like character disappears. So to the extent that objects behave classically is actually a measure of the entanglement that that object has with its environment. We're all, right now, deeply entangled with everything else. It's just that the laws of physics, or the construct of physics that we have in that regime of everything entangled with everything is just classical physics, is Newtonian physics.
So the more entangled you are, the more classical.
Exactly. If, and there's a really important part here, in that regime in which classical physics is dominating, the entanglement, although it's there and very complex and with every possible particle, is uncontrolled. We don't have the ability to turn it on and turn it off, or to have one quantum object entangled with another in a very precise, controlled way. If you're an electron and you're interacting with every other electron and you're entangled with every other electron, then you look like you're obeying classical physics. What we want to do with the quantum computer is be able to turn on that entanglement at a very precise point in time for particular particles in order to be able to share and couple those correlations, turn it off again. But it's that isolation that's the hard bit.
We might have time for one more question. So I haven't really gone in the middle here, so right there, yeah.
So the reason I applied to this is because I don't know what I want to do yet, but I think, I think a lot of people have this kind of dream of like what job they want, like perfect kind of each thing's perfect, but in reality, it's kind of like, well, every job's gonna suck at some point. So what determines, like, how do you go about finding a job and saying that's what I want, that's not what I want?
How do you find your dream career?
Trial and error. I mean, I think that Maya illustrated that pretty well, and I've done the same thing. I think you've got a lot of lifetime to try things out, and if you don't like it, you kind of know pretty quickly. And when you do like something, you'll be excited about it, and you'll want to keep doing it. I think it's also just important to, try different things. Like, someone asked how I wound up here. It was because there was an opportunity, and like, why not? Like taking new opportunities, trying to learn new things, learning about what other people do is also really important. Because even now, I don't really know what everyone does and what the scope of everyone's career is and like what everyone's job is. And I think there's probably always something better for you or more perfect for you. So I think it's just kind of an optimization problem.
I think it's also important to realize that the job I'm doing now didn't exist when I was your age. There was no quantum research job. It's not something that you could do in a commercial company then. Like, it was something maybe done by a couple of, I would say when I was your age, it was not even really done in a couple of labs. It was not done. It was done on paper by theoretical physicists. So don't be afraid that the fact, like, your job may not exist yet, or you may have to create your job to get something that you want. But for me, the guiding thing has always been finding groups of people that I felt excited to be around. It's not so much the work or wanting to, the work or what you're doing on a day-to-day basis, but it's been the people and then doing something together to try and build something. And then then you find another, you meet someone literally at a conference sometimes, or sometimes just like maybe at an airport, or all sorts of crazy stories I've got.
School full of 100 students.
Yeah, and you start a personal interaction, and you find out they're doing something interesting, and you think, I know a little bit about that, or I know nothing, but I'd love to learn about it. And all of a sudden, you end up working for them, or they end up working with you. To me, that sort of is how I've navigated.
It's less about doing what you love, more about doing things with people that you love, in a sort of way.
Well, there's lots of things you can do that as David said, not if you break things down right to the granularity of every 5 minutes. Is that 5 minutes? Did I love that? Probably not. But you integrate over months, years. And define what you love. For me, it can be lots of different things, but I could say the common characteristics of them are building things. So taking things from an idea of something that doesn't exist yet, and then building it and then seeing if it works the same as how we thought it might.
Yeah, so I guess, does that help a bit? Kind of focus on the things that you enjoy most, whether or not that's an existing career. Just whatever you do, put yourself in a position where you end up doing those things that you enjoy. Yeah,
and where you want to get out of bed and go to work.
Yeah.
Don't treat work like a chore. If you're doing a job and you don't want to get out of bed and don't want to go there, then maybe you should be doing something else and go and try it and go and find what it is.
Well, I think that's pretty much what we've got time for today, guys. So big round of applause for David, Maya, and Erin.